Hello everybody, this is going to be the last video about navigating the stars. And what we're going to do is going to take everything that we've learned about our local sky, our horizontal coordinates, our celestial sphere, and our equatorial coordinates, and try to put that all into perspective about what our sky actually looks like. This is going to be a pretty dynamic video where I'll be using slides and stellarium. Let's hope that this goes well. So, jumping in. Here we have a statement at the top that we are really going to be exploring. And we have the title that says, you can see what is above your horizon. No surprise, right? But now let's add a little bit more to that. Your horizon is determined by your latitude on Earth. So what I've done in this image here is try to give you a little bit of perspective to introduce a couple of concepts and what the bulk concept of what you can see in the sky, what is observable to you, depends on your location on Earth. It also depends on your time of year. We'll get into that whenever we talk about the annual motions of the Earth, its revolution around the sun. Or you have probably already read about it in the notes. If you haven't, these videos really do help. If you have already tried to go through these notes, I'm going to be talking through some of the animations and some of the trickier concepts because I know this content is particularly tricky. So here I have the Earth. And what I've done is I have this little picture of a little stick human that I made, and I've shrunk it down as small as PowerPoint will let me. And then I've drawn the local horizon for this person in green. And this is to help you realize that the Earth is really big and we're really, really small, which is why from our local view, it does seem like things are flat. That's because the Earth is so large that we can't observe the local curvature except in very, very ideal conditions on Earth. And the way that I've drawn this person right here, that looks like they're incredibly small, is actually 200,000 times larger than if it was a real person. So if that was a real person, that person would be 1.1 million feet tall. So typically, I'd have to, well, in reality, I have to draw this person so small, and then we'd just see something flat because we'd just be looking at a very local part of the Earth. A lot of this to say, in a lot of the diagrams that you're going to see, I draw the horizon going straight through the center of the Earth. And the reason that I'm doing that is, let's go back to our scaling to everything, the solar system fits inside the football field. The Earth was a grain of salt compared to how very, well, just scaling our solar system. And then you consider how far away the nearest star was, all the way in DC. The stars are so incredibly far away that in relative scale, the Earth is tiny, so we might as well not even consider it as anything other than a point. And that way it's best to do our geometry that we're going to have to play with by drawing the horizon going straight through the center of the Earth. The stars are very, 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 very far away. This is also why they appear fixed in the sky. Now I want you to imagine if I take this person and I move them to, say, a higher latitude. I'd redraw the horizon line, and now some of these stars would be below that horizon line, which means they wouldn't be observable from these higher latitudes. To really bring this point home, I want to go ahead and really just hammer in that your local sky, what is observable, really depends on your latitude on Earth. So now we have a ridiculously tall human. But for now, I'm going to draw the horizon still sitting on the surface just to show you, so you can see this person changing latitude. Remember that we can only see what is going to be above this green line, my local horizon. This purple line points towards the zenith, so this purple dashed line would actually represent our meridian. And we can only see things that are on the person side of the green line. Things below the green line are invisible, cannot be observed by this human. I shouldn't say they're invisible, they're just blocked by, the Earth is blocking them, so we can't see them. So as this person says, say, goes north, the stars that are observable from that latitude change. Now, these stars down here are below the horizon, but Polaris is now above the horizon. In fact, it's right at this person's zenith point. Oops, wrong button, but it's good to see that again. So as their latitude changes, the stars that are observable change as well. What is above the horizon based on your latitude on Earth changes. So what declinations is really what we're talking about. What parts of the celestial sphere, what declinations are observable depends on your latitude. So if we're going to talk about that, what we should do is start relating our two coordinate systems, our declination, our celestial sphere coordinates, the ones that actually give us locations of where the stars are, to our local coordinates, the ones that we live on a daily basis, our horizontal coordinates, our altitude and azimuth. So this is where we blend the two systems together. And I know this is difficult. Go through the notes, rewatch the videos as much as you need to, ask me questions because I know this is the difficult part. So what declinations are observable based on your latitude? What stars are up from where you live? If you go outside tonight, what declinations can you see? If you were to travel to the southern hemisphere and spend some time there, maybe in Australia, what declinations could you see there? What different stars, what different constellations would you see? All right, let's do waypoints. So always go back and try to figure out some easier stuff that will guide us to the more advanced stuff. And let's go with a statement. The declination of your local zenith is equal to your latitude. That is something, write that down 10, 15 times. I'm going to show you that. So this person right here is on the equator. So their latitude would be 0. Their zenith pointing out towards the celestial sphere, that would be the celestial equator, which definitely has declination of 0. It's easier to see if I go up to Knoxville. So moving this person 36 degrees, so a 36-degree angle right here, moving them up 36 degrees. And this zenith point that they're pointing at. So now I can have their local horizon, and this is 36 degrees. Project that out. So really, this right here is the line defining the latitude on Earth. Keep going straight through the top of that person's head, pointing straight up towards the zenith. And that would be just pointing right towards declination plus 36. Remember that we get our declinations by projecting our latitude out onto the celestial sphere. So if this is latitude 36, we just keep going straight, that's declination plus 36. It's 36 degrees above the celestial equator. So our zenith point, the point directly above this person's head, is declination 36. So the declination of your local zenith is equal to your latitude. Now, this sounds almost a little pedantic. The altitude of your local zenith, straight up is always straight up. The altitude is always 90 degrees. What we want to know is we want to use that information to start figuring out a couple of other things. So the declination of your zenith is equal to your latitude. And notice now we have a declination mapped onto our local sky. That's going to be our linchpin to figure out what declinations are observable. But we need to keep in mind that straight up is always straight up. That's 90 degrees up. So your zenith always has altitude of 90, two different coordinate systems. Your horizon always has an altitude of 0. All right. So I'll make another statement, and I'm going to be showing this one on the next slide. The declination of Polaris is always plus 90 degrees. Okay, that one is just another, we know that Polaris, if we're looking at the celestial sphere, here would have the celestial equator, we go up 90 degrees on the celestial sphere to hit Polaris. So Polaris has declination of 90. Plus 90. It is at the North Celestial Pole. Okay, putting all of our pieces together. And now we can do this to figure out that the altitude of Polaris, so what altitude is the North Star? How many degrees above the horizon do you observe the North Star? Is the same number of degrees as your latitude. We're gonna have to do a little bit of geometry to get there, but I'm not gonna ever require you to do geometry this kind of geometry for quizzes and exams. I know it's really, really difficult. I'm gonna try to walk you through a little bit of it so you can see that these declarative statements are making can just be derived by drawing a couple of lines and knowing some basic geometry. But realize how powerful of a statement that is. The altitude of Polaris, the number of degrees above the horizon, is the same number of degrees as your latitude. So here in Knoxville, we're at latitude 36. So Polaris is at altitude 36 degrees above the horizon. This is extremely powerful for navigation. All I have to do to figure out where on Earth I am is go outside, measure the altitude of Polaris. As long as I'm in the northern hemisphere, I can see it. And whatever that altitude is tells me my latitude on Earth. The altitude of Polaris equals your latitude. All right, this next part is for the curious. It comes up in the homework a little bit, so you might want to pay attention to that. But just one question to really help you hammer all these things in, and why we went through these exercises and some things that almost seems like tautologies, like the altitude of your local zenith is always 90 degrees, the declination of Polaris is always plus 90 degrees declination. This allows us to translate between our horizontal coordinates and our equatorial coordinates. So we can actually tell what declinations are observable from Knoxville. Clearly, declination 36 is observable since that is our zenith. Straight up from Knoxville, I'm pointing at declination plus 36. But this is also straight up. That's 90 degrees of altitude. What was the altitude of the southern horizon? 0. So there's 90 degrees between here and moving down to here. So if I want to figure out what the declination of my southern horizon is, all I have to do is take 90 degrees off of this right here. So I'd have 36 and subtract off 90 degrees, which would bring me down to minus 54 degrees. My southern horizon in Knoxville, if I point straight south at the horizon, I am pointing straight at declination minus 54. Going to the north, it's a little bit stranger because we can start from 36 and we have 90 degrees to move to our northern horizon from our altitude, from our zenith. There's 90 degrees of altitude there. So I add 36, but remember you can't go over 90. So I'll trace this out on Earth. I'm going from 36, spend 54 of it going up to 90. But if I go more north, I just start coming back down. So I'm now going down in latitude. But I went 54 here. That leaves 36 to go down. 90 minus 36 is plus 54. So if I point due north at the horizon, I'm pointing at declination 54. Keep those numbers in mind. It'll help whenever I come and demonstrate this on stellarium. Okay. Now, this last one, the altitude of Polaris, the North Star, is the same number of degrees as your latitude and the promised geometry. So now I've tried to shrink things out. Just as I was saying whenever I started this video, I'm putting the horizon. My local horizon is going straight through the Earth. I'm putting this person at 36 degrees north, so they are in Knoxville. And here's all my stars out here. And now let's start building our waypoints, just as we were doing before. All right, first one is I'm going to go straight out and figure out my local zenith. And now I know that my local zenith, I know that declination is plus 36. I'm just taking that latitude line and projecting it out. So plus 36 is the declination of my zenith. Now I can figure out, I can use this as well, the celestial equator. Project out is a declination 0. I can project the north celestial pole, the North Pole, project that out. That'd point directly to Polaris, so that's dec plus 90. Notice now I have some waypoints of declination going on, not just the 36. And what am I after? I really want to figure out what is the altitude of Polaris, because I'm saying the altitude of Polaris is your latitude. My latitude is 36, so this angle better be 36. Okay. We have 90 degrees between my horizon and your zenith. I know that this angle is 36 degrees. I know there are 90 degrees between dec 90 and dec 0. The celestial equator in the North Celestial Pole. So if this is 36 and this entire thing is 90, this needs to be 54 degrees. And if this is 54 degrees and I have 90 degrees between my zenith and my horizon, and this is 54, that means that this needs to be 36 degrees. All right, let's walk through that one more time, just because it's good to review this, because I know geometry is not everybody's favorite thing. I know my local zenith is at declination 36. I know that Polaris is at declination 90. I know that the celestial equator is at declination 0. I know there are 90 degrees between my line pointing towards Polaris and my line pointing towards the celestial equator. I know that at 36 degrees latitude, this angle right here is 36 degrees. To complete the 90 to get up to here, that would make this angle 54 degrees. If this angle is 54 degrees and there are 90 degrees between this purple line and this green line, then this angle must be 36 degrees. But this angle right here is just the number of degrees I'm pointing above the horizon. So the altitude of Polaris is 36 degrees. So I made use of some right angles there, and I made use of my knowledge of the declination of my zenith point is my latitude. And I made some waypoints using Polaris and the celestial equator to figure out what the altitude of Polaris is going to be. Notice I could also use the same line of reasoning. So if we have the 90 degrees here, if this angle right here is 36, then this is 54. What is 54 degrees below deck 0? Minus 54, and I'm back on my southern horizon. Or I could consider it this way. What is the altitude? So how many degrees above my local horizon would I have to look up to look at the celestial equator? I'd have to look up 54 degrees. Okay, I know that was a lot of information. What are you walking away with? The altitude of the North Star Polaris is equal to your latitude, and now you can navigate north and south on Earth. And I want to end just by doing something I maybe should have done whenever I was talking about equatorial coordinates. So here I'm going back to my slide about equatorial coordinates that I was showing you in the previous video. And I want to go ahead and show you what to expect when we switch to a stellarium view. So here we have the Earth, and I have this orange line is marking 36 degrees above. So this is marking where Knoxville would be on the Earth. And what I'm going to do is I'm going to draw my horizon going directly through the Earth. So this would be my Knoxville horizon right here. And now I could just literally read off all the declinations that are observable. So I know that Sirius would be observable. And I can see everything from minus 54 to plus 54. So if the declination is between minus 54 and plus 54, I can observe all of these stars, which I can. You see that Arcturus looks like it's below the horizon, but remember this is rotating around and around and around. So I could have drawn it equivalently this direction, and it would be above the horizon. It's only this cone down here that is not observable. Okay, a bit of an aside, but let's go ahead and take a look at what's above my horizon for this time of day. Here we have that 36 degrees up to Polaris. So whenever I go to my declination view, and I want you to imagine that here you are standing, put yourself right here, looking out, what would this grid look like? Well, I should see a bunch of concentric rings, my declination rings, around Polaris right here. So I should be able to picture what this grid would look like if this were my local horizon. And that's exactly what I'm going to try to do right now as I switch over to stellarium. So stop that share and share stellarium, which I've set up, and I should be able to reinforce some of these concepts. So here we have stellarium. I have set it all up. So here's our date and time. This is tonight at 10 p.m. If you go out at 10 p.m., here we are standing in Knoxville. Oh, now I can almost picture that grid. I'm looking out towards Polaris, the North Celestial Pole. There's Polaris. and I'm looking up to where all those grid lines are converging, if I let time go ahead and rotate and speed up, I can see everything's rotating around that. My horizon would be spinning around and around and around that 2D view I was giving. Make sure I'm going to turn off the atmosphere here. Now you can see everything is rotating around and around and around. And if I was right, I'm going to go ahead and stop time because I want to actually point at a certain point on the sky. So the altitude right here of Polaris, I can go over here. It gives all sorts of information. Altitude, 36 degrees, check. All right, so we can check that the altitude of that one is 36 degrees. I said that the northern horizon should be declination 54. Let's just click close to the northern horizon. Find something that's near the northern horizon. It should have a declination of 54 degrees. Check. And now we just have to check the southern horizon, which should be minus 54 degrees. And go ahead and sort of picture, you can see that grid, the 2D picture now becoming a more sort of immersive 3D view. Click on the southern horizon. So something very close to the southern horizon should have a declination that is near minus 54 or so. I'm a little bit above it there. Let's see. Getting close. Yeah, right down near minus 54. There's a little bit of stuff obstructing my view of the horizon right there. But hopefully that confirms all the geometry I was showing you with the slides. And now you can see what that grid looks like with a little bit of additional information. And you know all the declinations of the stars that are observable. What right ascensions are observable depends on your time of year. That is a conversation that is much deeper. The things that you really need to know for this class are the altitude of Polaris and the declination of your zenith. Why those things? The altitude of Polaris is great for navigation. It lets you know what latitude you are on Earth, so just a useful skill. And the declination of your zenith is sort of that linchpin, that first identifying the declination of your zenith, which has altitude 90, was the first thing that we did that allowed us to figure out everything else, that told us that all the observable declinations from Knoxville are from minus 54 dec to all the way up to 90 dec. All right, I know that's a complicated video. Please request if you want more information. Hopefully some of this is starting to sink in. Thanks for tuning in.